Hi, Algebra 2 students. We're going to continue our probability unit. Today, we're going to be focusing on the word and what the word and will mean in a probability problem. Remember, yesterday we talked about or, which told us to add, and is going to be a key word that means to multiply. And as we talk about the lesson, most of it is going to be pretty straightforward. We're doing some straightforward multiplying, but there will be some special situations where we have to be careful what we are multiplying. That's going to be the key for today is recognizing when it's an easy multiplying, we're going to have to be careful and change things up. But before we begin, we're going to look at a flashback from the statistics part of this unit because our test next week on Monday will have both probability and statistics on it. So if we remember back, we saw problems like this that dealt with averages. The average of five numbers is 8. So here's what I know. If I add up all five numbers and divide by 5, I'm going to get 8. Now my numbers are -2, -1, 4, 10, and x. So what is that missing number? So remember, the way that we solve any average problem is we add up all the numbers and we divide by however many there were. Now there are 1, 2, 3, 4, 5 numbers, including the one that we don't know, and I know what I'm supposed to get for my answer is 8. So this is the problem that I set up. And anytime you have a missing number problem, it's always set up the same way. Add up the ones that you know, plus the missing number x, divided by however many there would be. Now, after I set this up, I do this little bit of adding. I do -2 plus -1 plus 4 plus 10. And when I do that, I get 11 plus x divided by 5 equals 8. And our key for solving this was to say, hey, I don't like that division. I'm going to multiply by 5, which cancels out the denominator. But what I do on one side, I do on the other. So 11 plus x equals 40. Minus 11 on both sides, and we get that x equals 29. If we wanted to double check that answer, we could find the average of -2, -1, 4, 10, and 29, and we would find that it would be 8. So as part of our flashback, here's a your turn. I went miniature golfing 4 times. Here are 3 of my scores, and I'm giving you my average. So what did I have to get on that 4th round by missing round my x? So go ahead and set this problem up. Write down your answer on a piece of paper somewhere, and when you have your solution, type it into the box to let me know how you did. Hopefully you got for your answer 54. Here's my setup. I added them up, plus x divided by 4. Those three numbers, when you added them, were 150. Did my multiplying and my subtracting. Okay. Now, the main part of our lesson today is not the statistics flashback. The main part is and probabilities. But before we get there, we have two little miniature parts that are kind of leading the way. The first is called the fundamental counting theorem. Now, anytime you see the word fundamental, that's usually a key that, like, hey, that's a big deal. We don't throw the word fundamental around willy-nilly in math class. Okay, fundamental is something that's really important. And the fundamental counting theorem says this: if event m can occur m ways, and event n can occur n ways, then there are how many possible ways to combine those? So the event m followed by event n can occur m times n ways. So if I have 2 pairs of pants and 3 shirts on vacation, how many possible outfits do I have? So I have 2 pairs of pants, 3 pairs of shirts. How many outfits? Well, I would multiply those two numbers together. 2 times 3 gives me 6 outfits. 6 outfits. Now, why is that the case? Let's say I have 2 pairs of pants. I call them P1 and P2. And I have 3 shirts. I call them S1, S2, and S3. Well, each pair of pants can go with each shirt. And so that gives me 6 total combinations. I could do pant 1 and shirt 1, pant 1 and shirt 2, pant 1 and shirt 3. Or I can do pant 2 and shirt 1, pant 2 and shirt 2, and pant 2 and shirt 3. That gives me 6 total options here. And it's annoying to have to list all those out. So it's a lot easier to say the number of options you have for the first times the number of options you have for the second. That is especially helpful when we get to things like license plate. In Pennsylvania, the standard license plate has 3 letters followed by 4 one-digit numbers. How many possible standard license plates are there? Well, if we think about it, how many options do I have for the first part of a number of the license plate? Well, if it's a letter, there are 26 letters. So I have 26 different options for that first letter times 26 options for the second letter times 26 options for the third letter. So the fundamental counting theorem tells us that for each um, part of the license plate, how many options I have. Now, for the second four parts of the license plate, we're talking about one digit numbers. And how many one digit numbers are there? There's 10 of them: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 10 options times 10 options times 10 options times 10 options. So when you're talking about making a license plate, the fundamental counting theorem tells us there are 26 ways to choose the first letter, 26 ways to choose the second letter, times 26 ways to choose the third letter, times 10 ways to choose the number, then the next number, the next number, and the next number. If we multiply those all the way out, we're going to get our total number of options. So 26 times 26 times 26 times 10 times 10 times 10 times 10. And we end up with, this is crazy. There are, if you multiply it all the way out, looks like 175,760,000 license plate options just using that standard formula. So I don't think Pennsylvania has to worry about running out of license plate options soon, because our population is only about 12 million people. Similar idea here. A pick three lottery involves picking three one-digit numbers correctly. So how many possible combinations are there? Well, there are 10 ways that you can get the first number, 10 ways for the second number, and 10 ways for the third number. So if you multiply those all together, you end up with 1,000 combinations. So if you're playing the pick three lottery, there are 1,000 different combinations that you could choose. Now, the pick three lottery usually pays out about maybe $100. It costs $1 to play. You win it, you get $100, $200. Not a huge payout. Why? It's only 1,000 different combinations. So if you play the lottery and you buy one ticket for the pick three lottery, you have 1,000, 1 in 1,000 chance of winning. Now, bigger lotteries like the Powerball that have more payouts have millions of combinations because instead of picking one digit numbers, you're picking numbers from like 1 to 56. So there's a lot more possibilities there. Okay, your turn problem is this. A high-end burger joint has 5 options for the bun and 8 options for the type of burger. How many bun burger combinations do you have? Okay, so maybe you've got for the bun, you've got sesame seed, you've got plain, you've got Kaiser roll, you've got sourdough, I don't know. 8 options for the type of burger. Maybe it's a cheeseburger, bacon burger, who knows? 8 options there. How many bun burger combinations do they have? Type your answer in the box. Okay, so hopefully you said, oh, it's going to be 5 options for the bun times 8 options for the burger. So 40 total options. 40 options there at that burger joint. Okay, the other little piece of the lesson we need to have before we can start the main bulk part of our multiplying is this. When the occurrence of one event affects how a second event can occur, the events are dependent. Otherwise, the events are independent. So determine whether the outcome of each trial is dependent or independent. Think about this. If I roll a number cube, if I roll a dice, does it matter what number I get? Will that affect the spinner at all? I mean, think back to that spinner that we did yesterday in our live session. Would it matter what number I rolled on a dice? Would that affect the outcome of the spinner? No. And so those events are independent. Those events are independent. What about picking one card from a deck, keeping it, and then selecting another card? Well, if I pull a card and it's the ace of spades, and I keep it in my hand and I go to select another card, didn't that change things? There's no more ace of spades in that deck anymore because I'm holding it. So I changed that deck by keeping the card out. Anytime I don't replace the card, it's a dependent event, and dependent events require special circumstances. They require us to do special multiplication when we do our calculations. How about this? Flipping a coin and getting heads, flipping the same coin and getting tails. Does flipping the coin the first time have any impact on the coin the second time around? No, no. So those events are independent. They have no impact on each other. Knowing one does not affect the outcome of the other. Well, if events are independent, that means if we want to find the probability of both of them occurring, we can multiply. And so that's our big rule here for today. To find the probability of two independent events both occurring, we multiply them times each other. And the key word is this. If they're both going to occur, it's an and. In the box on your note sheet, I want you to write the word and. Generally, when we're going to see problems like this, we are going to see the word and pop up or the word both. Whenever you see that, either of these keywords, that tells you to multiply the probabilities together. So example 4, what's the probability of rolling a 3 with a number cube and then rolling a 4 on the second roll? So the probability of getting a 3 and a 4 on the next roll is the probability of a 3 times the probability of a 4. Well, the probability of rolling a 3 is 1 in 6, and the probability of rolling a 4 is 1 in 6. So if I multiply that together, I multiply the top, multiply the bottom, now we get 1 in 36. There's a 1 in 36 chance of rolling a 3 and then rolling a 4. Let's change it up a little bit. What's the probability of rolling an even with a number cube, then, or you can put the word and then rolling a 5? Well, the probability of rolling an even and then a 5 is going to be this. Probability of rolling an even, there are 3 even numbers, 2, 4, and 6 out of 6, times the probability of rolling a 5 is 1 in 6. So we have a 3 in 36 chance or a 1 in 12 chance of rolling an even number and then rolling a 5. For example 6, let's take a look at this. What's the probability of tossing 3 heads in a row? Well, the probability of tossing 3 heads in the rows is the same as doing probability of heads and the probability of heads and the probability of heads. The probability of getting heads 3 times in a row is the probability to get heads, and I get heads, and I get heads. So that would be 1/2 times 1/2 times 1/2, which is 1/8, or 0.0125. Sorry, 0.125. 0.125. Now, the probability of getting heads 3 times in a row is 1/2 times itself 3 times. So the probability of getting heads 10 times in a row is going to be 1/2 to the 10th power. Now, that's because it would be 1/2 times itself 10 times. And if I did that on my calculator, if I did 0.5 to the 10th power, I get such a small decimal number that my calculator doesn't really handle it well. I end up getting 0.00097. It is so unlikely that I'm going to get heads 10 times in a row that it's 0.00097. That's crazy small. Very unlikely to get 10 heads in a row if you're flipping a coin. Okay, what I want you to try to do is answer these two questions. The probability of rolling a number cube and getting a number greater than 2 on the first roll, and then getting a 6 on the second roll. So this is an and then in a coin collection, 10 coins, 5 are pennies, 3 nickels, 2 dimes. What is the probability of selecting a penny, putting it back, and then selecting a nickel? I want you to answer those questions and put your answers in the box for me. Okay, probability of rolling a number cube and getting a number greater than 2, that'd be a 3, 4, 5, or 6. So that's a 4 out of 6, times getting a 6 is a 1 out of 6, which gave me 4 out of 36, which is 1/9. So if you had an answer of 1/9, that's great. Or you could do 0.1 repeating. In our coin collection, the probability of getting a penny was 5 out of 10, times the probability of getting a nickel and then getting a nickel, which was 3 out of 10. Now, if you just type this into your calculator as 5 divided by 10 times 3 divided by 10, that would be perfect. You would get 0.15 as your answer. So if you're doing this on the calculator, you can just type in 5 divided by 10 times 3 divided by 10, and you'll get our answer, 0.15. If you did it using your fraction knowledge, it'd be 15 out of 100, which would be 0.15. And we said we we're going to like decimals a lot in this unit. So let's look at example 7. A and B are independent events. Find the probability of A and B. So what does that mean we're going to do? That means we're going to multiply. We're going to multiply 5/8 times 1/4. Anytime you see and, it's telling us to multiply. And so what I want you to do is literally get out your calculator, if it's your phone, if it's your Chromebook, whatever it is, type in 5 divided by 8 times 1 divided by 4. Just make sure that your calculator is giving you the same answer as me. In this case, I got 0.15625. I'll stop at 0.156 as my answer. How about this one? Probability of A is 0.27. The probability of B is 0.38. The probability of A and B, well, we multiply them. 0.27 times 0.38. Just literally do that multiplying, and you're going to get your answer, and it will always be smaller than either of these answers. My answer was 0.156. 1026. If it's 4 decimals or less, I write it all the way out. If it's more than 4 decimals, I usually round it or truncate it, stop it after 3. One thing we have to be careful about is with percents. If you multiply the percents together, that won't give you a good final answer because it'll be more than 100%. So before we can multiply, we have to turn these into decimals. So remember, the way you turn a number into a decimal is divide by 100 or move the decimal point over 2. That means my decimal here is 0.15 and 0.60. So the probability of A and B would be 0.15 times 0.60, which is 0.09. And that would be my answer. If you wanted to turn it back into a percent, multiply it by 100, and you would get 9%. Okay, for letter D, the probability of A is 75%. The probability of B is 0%. What's the probability of A and B given the following? Well, that'd be 0.75 times 0. So 0.75, because 75%, turn it into a decimal. And when I do that, I get 0 for my answer. So if the probability of B is 0%, the probability of A and B will also be 0. Let's look at, and by the way, going back to this, you'll see on your practice worksheet today that there are some problems that look like this. And you just have to do that multiplication. That's about as easy as it gets. What I want to do is look at some of the slightly more complicated problems. So I'm going to open up a bag of M&Ms, and I count the number of each color, and I record it in a table. So my red, orange, green, yellow, brown are over here. So the first thing, before I even read the rest of the problem, how many M&Ms were in that bag? So I'm just going to add up 15 plus 10 plus 5 plus 12 plus 8. I got 50 total M&Ms. So if I select an M&M, put it back, and then select another, what is the probability I select a green and a red? Now, did you notice that I select the M&M and then I put it back? That means I replaced it. So both times I go to pick the M&M, there's still 50 M&Ms in there. So what I see that I select a green and a red and tells me to multiply. So the probability of selecting a green was 5 out of 50 times, because it's an and, the probability of picking a red was 15 out of 50. Show this setup. I don't just want a decimal answer. To get credit from me on the practice today, you have to show the multiplication setup. If you don't show that, you will not get full credit for that homework. Now, type this in. Make sure that you're typing these in on your calculator correctly before you're doing them on your own. So I would just type in 5 divided by 50 times 15 divided by 50, and I would get 0.03 for my answer. Now we look at letter B. I randomly select an M&M, I put it back, and then I select another. Notice, again, I'm putting it back. So I'm replacing it. What is the probability that I select a green and a green? Well, the probability of selecting a green was 5 out of 50, and means multiply 5 out of 50 again. Because I replaced it, there's still 50 M&Ms in there. Well, go ahead and multiply 5 divided by 50 times 5 divided by 50, and we should get 0.01. So the probability of me selecting a green and then putting it back and selecting another green is only 0.01. It's only a 1% chance of that occurring. Now, in letter C, notice those key words that it says here. All of a sudden, it's going to say without replacement. So I'm selecting an M&M and I'm not putting it back in. It's like I'm popping it in my mouth and eating it. I'm putting it on the desk next to me. When I do that, when I don't replace, that changes things for the second probability. So what is the probability I select a brown? Then then is a word that means and. Select a brown and then a yellow. Well, the probability of selecting a brown was 8 out of 50 times yellow. There were 12. But remember, I didn't put my brown M&M back in, so now there's only 49 M&Ms in the bag. 8 out of 50, but I kept the brown M&M, so now it's 12 out of 49. And that's the key, is that the denominator changed. Go ahead and do that multiplying. 8 divided by 50 times 12 divided by 49 gives me 0.039 as my answer. 0.039. Okay, letter D. randomly select an M&M, then without replacement, I select another. What is the probability I select 2 red M&Ms? Well, the first time there were 15 out of 50 M&Ms were red. But I picked out a red and I put it off to the side. So how many red M&Ms are still in the bag? Right. Only 14 red M&Ms were still in the bag. And how many M&Ms total were in the bag? 49. So what happened here is because I didn't put that red M&M back in, I changed the numerator and the denominator. When it's without replacement, I'm changing things. It's now dependent, and so I have to change things. So I do 15 divided by 50 times 14 divided by 49, and I get 0.086 or 0.085. And remember what I said, I have to see the multiplication and the final answer. Just the final answer is not going to get you full credit on the homework. In fact, if you turn in that homework and you don't have the multiplication, the highest you're going to get is a 3 out of 5 because you didn't do all the work I wanted to see. Okay, here are your turn problems. Parts A, B, and C. What I want you to do is to type in your answer to just part A, and then it'll reveal the answers to all three. So do all three, and then type in your answer to A, and you can see all the answers. Okay, so part A was without replacement. That meant that the denominator changed here for the second one. So freshman, there were 21 out of 65. For the sophomore, it was 19, but now only 64 because it was without replacement. For letter B, selected 3 players without replacement. Without replacement, what was the probability I selected 3 seniors? Well, there was 10 out of 65 for the first person, but then because that senior, I took his name and put it off to the side, there were only 9 seniors left out of the 64 people. Then, because I then also put that senior off to the side, I was down to 8 out of 63. Multiplied those all together and got 0.0027. And then finally, letter C was with replacement. That meant the denominator didn't change. So a senior and then a junior. Remember, then is like our and word. 10 out of 65 times 15 out of 65. The last type of problem I want to do today is a tree problem. And tree problems come up anytime you see the word of those. Of those, as soon as you see that, it tells us make a tree. So a school compiled the following data about former students who were juniors 10 years ago. 85% graduated from high school. So here was all the juniors. Of that, 85% graduated. So if 85% graduated, how many were left over? How many didn't graduate? Well, 100% minus 85% gave us 15% that didn't graduate. And notice how I'm turning these into decimals on my tree. So I defined the other number, you subtract it from 100. So 85% graduated, 15% didn't graduate. Okay, 15% didn't graduate. Now, of those that graduated, so now I'm in the top branch here. Of those who graduated, 90% are happy. So I have people that are happy and not happy. 90%, so that's 0.9, are happy. That means 10% aren't. So that's going to be 0.1 right here. Of those who didn't graduate, only 60% are happy. So I've got my happy branch and I've got my not happy branch. 60% of those who didn't graduate are happy, which means 40% are not. The final step on a tree problem is to multiply across the branch. So I'm going to multiply 0.85 times 0.9, and I'm going to get 0.765. That's the percent of people that have graduated and are happy. Now I do 0.85 times 0.1, and that gives me 0.085, which is the end of this branch. 0.15 times 0.6 is 0.9. So I'm multiplying this branch times the top, then 0.15 times 0.4, which gives me 0.06. If we add up all four of these numbers, we should get 1. And right here, that zero point 0.9, that should have been 0.15 times zero point 0.6, should have been 0.09. I missed the 0 in there. So put that 0 in there. Now, if we add up all three of these numbers, we're going to end up getting 1. So we can use that to answer questions. What is the probability that a person graduated and is happy? So what line up here is someone who graduated and is happy? We'll look at my branch. Here's graduated and happy. That's this person right here, that group, which is 0.765. What is the probability that a person is happy with their job? It's the probability that a person is happy with their job. Well, the probability that a person is happy, there's two branches. There's the 0.765 and there's the 0.09. We have to add those together. So both of those end branches are people that are happy with their job. And if we add those together, we get 0.855. With a tree diagram, the tricky part is trying to fill in the different parts of the tree. We always want to fill them in as decimals, and then you multiply to get the end. So in the your turn over here, what you need to do is fill in all the blanks on your paper and then multiply across to get these answers. And I want to know the probability of full size, which is the final answer. That's what you're going to try to type in for me. So go ahead and type that in after you've done the tree and done all that multiplying. Okay, a few things to notice. If 60% of the candy was chocolate, that means the rest was fruity. 100% minus 60% was 40%. So 60%, 0.60 was chocolate. The other 0.40 was fruity. Of the chocolate, 0.75 was snack size. That meant that 0.25 was full size. So 100 minus 75 was 0.25. Same thing down here, 45 was snack. That meant that 0.55 was full. Multiplied across the branches to get these answers, 0.6 times 0.75, 0.6 times 0.25, 0.4 times 0.45, and 0.4 times 0.55. So what was the probability of getting something that was full size? I added together these two branches that ended in full size. So today on this Your Turn, I kind of gave you the tree and had you fill in the missing parts. Tomorrow, one of the things we're going to practice is giving you a chance to write the whole tree diagram from scratch. Okay, so what's next? Do the practice worksheet. I did give you the answers today, so you should check your own and make changes before you submit it. Okay, don't just copy down my answers. That won't help you when it comes to the quiz, to the test, or to the Keystone in January. So make sure you do it, check your answers. And then just a reminder that there is a live session on Friday at 12:45. That's going to be the bulk of our class that day. I'm not going to post a video that day. Most of our lessons going to be live, and then a little bit of a test review for you to do on your own that day. Okay, thanks for watching and have a great evening.